Okay, good morning everyone. Today we'll take a look at linear programming problems, section 3.4. This is the last section before you have your tests on Wednesday and Thursday. Your tests will cover everything, including 3.4. VLA students expect to test either Wednesday or Thursday. In this coming weekend, you will have a take-home test on a linear programming word problem, which I'll go over with you today. On your test on Wednesday or Thursday, you'll have a linear programming problem, but it will not be a word problem, and I'll go over those with you today as well. So let's take a look at what linear programming is. Linear programming is a method of finding a minimum or maximum value of a function that satisfies a given set of conditions called constraints. Okay, so let's take a look at a word problem involving linear programming. So here we have Leela. She's selling hot dogs and hamburgers at the senior cookout. She has $80 for hot dogs or hamburger buns. Each hot dog or hamburger bun costs $1. She has $100 for hot dogs or hamburgers. Each hot dog costs $1 and each hamburger costs $2. Leela can sell hot dogs for $2.75 and hamburgers for $3.50. How many hot dogs and how many hamburgers should she sell to maximize her profit? So here I've defined the variables. I said let x equals the number of hot dogs and let y is equal to the number of hamburgers sold. And now we have two constraints. One constraint is she only has so much money to buy buns. Okay, each hot dog bun costs $1 and each hamburger bun costs $1. So x plus y must be less than or equal to 80. She only has $80 to spend on buns. Now, if she buys all hot dog buns, she can buy 80 of them. 80 divided by 1 is 80. So I'll mark that on my coordinate plane. So on the x-axis, I have hot dogs. On the y-axis, I have her hamburgers. So for the buns constraint, if she bought all hot dog buns, she could buy 80 of them. So that point right there, so that's 80 and 0. And then if she bought all hamburger buns, again, she can buy 80 of those. Okay, 80 divided by 1 is 80. So she could buy 80 hamburger buns. And that would be the point 0, 80. So 0 hot dog buns, 80 hamburger buns. Or she could buy 80 hamburger buns, or 80 hot dog buns and 0 hamburger buns. So if I draw my line there for the first constraint, the bun dollar constraint, she has to be, or you have to be, below that line. Okay, any point below or on that line satisfies that constraint. So for example, if you're at the origin, certainly 0 times x, or 1 times 0 plus 1 times 0 is less than or equal to 80. So you have to be below that line. You cannot be at like 40 and 60, for example. So that's the point 40 and 60. Because 40 times, so 1 times 40 is 40. And then 1 times 60 is 60. And that is not less than or equal to 80. That's okay. So you can be over on this side of the line. All right, so you have to be, okay, so you have to be below that line. And then we can do the same thing for the meat constraint. So again, if she bought all hot dogs, each hot dog is $1, so she could buy 100 hot dogs. Okay, so that would be the point. Let me mark. So that would be the point here. So this would be she could buy all hot dogs and no hamburgers. Or she could buy 50 hamburgers. 100 divided by 2 is 50 if she bought 0 hot dogs. So the other point is she can buy 0 hot dogs but 50 hamburgers. And again, I'm using constraint number 2. And let me mark this here. So this was so this was my bun constraint, and then I'll mark my meat constraint here. Okay, let me make that a little clearer. Okay, So that's my me constraint there. And again, you have to be below that line as well. Now the other constraint we have is what's called the non-negative constraints. Both x and y must be greater than or equal to 0. So I have to be above the x-axis and to the right of the y-axis. Alright, so my feasible region is I have to be both below the green and the blue line, and then I have to be above the x-axis and to the right of the y-axis there. So that's my feasible region. Any point in that feasible region is a solution. All right, so we graph the feasible region for those constraints. Now, she wants to maximize the number of hot dogs and hamburgers she can sell. And so the objective function here is she wants to maximize her profit, if you will. Her objective function in each hot dog she can sell for $2.75, and in each hamburger she can sell for $3.50. Okay, and that's what the problem said. Now the thing is, with a linear programming problem, you maximize or minimize the objective function at what's considered the corner points of the feasible region. Well, one corner point is 0.50. The other corner point is right here. Again, the corner point of the feasible region is 80, 0. Another corner point is 0, 0, which is right here. And so the last corner point is we have to figure out the intersection there. The corner point of that feasible region. Well, that's a solution to two equations, to my constraint equations. Equation number 1 and number 2. So I have x plus y is equal to 80, and then x plus 2y is equal to 100. Okay, so that's my system of equations. I can use elimination or substitution. I'll just use elimination. I'll multiply the top equation by -1, so that will give me negative x, negative 2y equals negative 80. And then if I add, I would get, oops, that should be negative y. So if I add, I get y then is equal to 20. So y would be 20, which would make x 60 from this equation here. If I substitute that up into there, so I'd get x plus 20 equals 80, x equals 60. Oops, so my other corner point is 60, 20. Okay, which is what I have there. Now, if I evaluate the objective function at each of these corner points, okay, and I look to see where it's the largest, because that's what she wants to do. She wants to maximize her profit. Her profit equation is 2.75x plus 3.5y. So the largest value is 235. So she should sell 60 hot dogs and 20 hamburgers, and that would maximize her profit. So that's it for linear programming. You have constraints, and then you have an objective function, and you want to maximize or minimize something according to the objective function given the constraints. And again, and that always happens, the minimum or the maximum always happens at the corner points, always. It always happens at the corner points there. Okay. So 0, 50, 0, 0, 60, 20, and an 80, 0. So let's look at some plain vanilla problems, no word problems, but the problems you will have on your test. You have a problem like this, it'll be a take-home test over the weekend, word problem, linear programming, but then you'll have plain old vanilla problems. So let's just take a look at two of them. So let's say here I have, these will be problems you'll have for homework tonight. So example number 8, for example. I think this was one of your homework problems from the night before. So I have a system of 3 inequalities. Y is less than or equal to 7, and I've graphed it there. So that's the line y is equal to 7, but y is less than or equal to 7. You have to be below that line. Okay, so that's equation number 1. The other equation is y is greater than or equal to 2x minus 3. So my y-intercept is negative 3. Right there. And my slope tells me to go up to 1, 2, and over 1. Okay, so and then I draw that line. So that's the equation y is equal to 2x minus 3. That's equation number 2. And that says I have to be above that line. I have to be above it. And then the other equation, equation 3, again my y-intercept is negative 3. And here I go down 1 and over 2. So down 1 and 1, 2, and over 2. And I draw that line. So that's the equation y is equal to negative 1/2 x minus 3. That's equation number 3. And that says I have to be above that line. Okay, so my feasible region then is I have to be below the line y is equal to 7, above the line y is equal to 2x minus 3, and above the line y is equal to negative 1/2 x minus 3. My objective is to minimize, so I have my objective is to minimize p is equal to 2x minus 4y. So I have to find all the corner points of that feasible region. This one is easy to see. That's the point 0, negative 3. So that's the point 0, negative 3 there. This corner point here, that's the intersection of two lines. One is y is equal to 7. I can see that. The other one is y is equal to negative 1/2 x minus 3. So you said y is equal to y. So 7 equals negative 1/2 x minus 3. Add 3, you get 10 equals negative 1/2 x. And then multiply by negative 2, and you get negative 20 equals x. So this is going to be then negative 20 for x. And of course y is equal to 7 at that point there. Okay, so we had the point 0 minus 3, and then negative 20, and then 7. And then lastly, we have to find this corner point there. So again, that's a system. We solve a system of two equations. One is the line y is equal to 7, and the other is y is equal to 2x minus 3. Okay. 2x minus 3. And then again, I said y is equal to y. So 7 equals 2x minus 3. So 10 equals 2x. And then 5 equals x. So this is a point 5 and 7. Okay, so I found all of my corner points there of that feasible region. And then I evaluate the objective function 2x minus 4, 3. I want to minimize it, so I'm looking for this where I get the smallest value. And that happens at the 0.57. I get negative 18. Okay. And again, you'll have problems like this on your test, the plain vanilla problem, so I'll go over one more. Alright, for homework, so you know how to do these, I'll do number 3 with you, and I expect to see this on your handwritten work because it is guided practice. We first have to graph the feasible region, so I'll do that. So this is number 3. This says that x has to be greater than or equal to 0, so I have to be on that side. Y has to be greater than or equal to negative 1, so I'll draw my line y is equal to negative 1, and I have to be above there. And then y has to be less than or equal to x plus 1, so my y-intercept is 1. My slope says go up 1 and over 1, up 1 over 1, or down 1 over 1. And then I can draw that line. So let's see here, this is y is equal to x plus 1. It always helps to write your equations on your line, so you know what you're working with. X is equal to 0 and y equals negative 1. Okay. And then lastly, I have to draw, so let me just highlight that. So this was y equals x plus 1. And then this was y equals negative 1. And then lastly, I'll do this one here. Oops. So my y-intercept is 6. I start at 6. And my slope says go down 1 and over 4. 1, 2, 3, 4. And down 1 and over 4. 1, 2, 3, 4. Okay, and then I'll draw that line here. Yeah, and that says I have to be below that line. And of course I have to be below that line because it says less than. Y is less than x plus 1. I have to be below that line. And then y is less than or equal to negative 1/4 x plus 6. I have to be below that line. And I have to be to the x is greater than or equal to 0 and y is greater than or equal to negative 1. So my feasible region then is all of this here. Alright, that's my feasible region. Now let's find a corner point. Some of these will be easy to find. So what is that? That is the point 0, minus 1. This is a point, so that's a corner point. This is the point 1, 0. No, x is 0, 1. I have to find this corner point here. Well, that's the intersection of two lines. That's the intersection of the line. Let's see here. I guess you can almost see it from the graph. What's said about 4, 5, but let's verify. It's always good to verify. That's the intersection of the line y is equal to x plus 1. And then y equals negative 1/4 x plus 6. So let's set y is equal to y. Easiest substitution problem you ever have. So x plus 1 equals negative 1/4 x plus 6. If I add 1/4 x to both sides, 1 and 1/4 gives me 5/4 x plus 1 equals 6. So 5/4 x equals 5 if I subtract 1. And then if I multiply by 4/5 both sides, I would get x is equal to 4, which I can certainly see there. X is equal to 4. So this is the point. X is 4. And of course, if x is equal to 4, I can just substitute in. I can substitute in here if x is 4, and I get y is 5. And I can certainly see that. Okay. So that's a corner point. And then we have one more corner point to calculate, and that's going to be way over here somewhere. Okay, which that went off the graph. So we just use the two equations we have. One equation is y is equal to negative 1. Okay, see this one is going to be, it's going to go way off the graph. And the other equation, what's that one there? Oh, this is the equation y is equal to negative. So this is y is equal to negative 1/4 x plus 6. And that's the equation y is equal to negative 1/4 x plus 6. So we want to find the intersection of the two. Okay, so we said y equals to y. So we have negative 1 equals negative 1/4 x plus 6. And then if I subtract 6 from both sides, I get negative 7 equals negative 1/4 x. And then multiply by negative 4, I get 28 equals x. So over here, this would be the point. X is 28. And of course, then y is negative 1. Okay. We knew y was negative 1 because that was one of the equations we had for our system of equations. Y is equal to negative 1 and y is equal to negative 1/4 x plus 6. So I found all of my corner points. 28, negative 1, 0, negative 1, 0, 1, and 4, 5. And we want to minimize this. So when I substitute in those corner points into my objective function. The smallest value I get is -5. Right there. So 0, -1 will give me the minimum value. Okay, so you'll have a couple problems like that for homework. Oh, so just so that you know how this works here, you'll have 2, 3, and 4 to do, 5, 6, and 7. So I've already done 3 and 5 with you, or 3 and 6, I'm sorry, because 6 goes with exercise 3. But again, make sure you have that on your handwritten work. Okay, so I've done 3 and 6. So 5 will go with 2. You'll maximize the feasible region for number 2, for 5, and for 7. You'll minimize. So you have to draw the feasible region. You have to draw the system of inequalities, the feasible region. Find the corner points like I did for number 3. And then evaluate those corner points. And then you'll do 9 and 10 as well. 11, and then 12 goes with 9, and then 13, I believe, goes with 10. So you'll do 9, 10, and 12, and 13, but they come in pairs. Okay. So there. And again, your test on Wednesday, Thursday will have these plain vanilla problems. You're given some y is equal to mx plus b. You have to graph them, and then you're given an objective function, and then you have to minimize or maximize the objective function after you find the corner points of the feasible region.